A plate heat exchanger is a type of heat exchanger that uses metal plates to transfer heat between two fluids. This is a major advantage over a conventional heat exchanger in that the fluids are exposed to a much larger surface area because the fluids spread out over the plates. This facilitates the transfer of heat, and greatly increases the speed of the temperature change. Plate heat exchangers are now common, and very small brazed versions are used in the hot water sections of millions of combination boilers. The high heat transfer efficiency for such a small physical size has increased the domestic hot water flow rate of combination boilers. The small plate heat exchanger has made a great impact in domestic heating and hot water. Larger commercial versions use gaskets between the plates, whereas smaller versions tend to be brazed. The concept behind a heat exchanger is the use of pipes or other containment vessels to heat or cool one fluid by transferring heat between it and another fluid. In most cases, the exchanger consists of a coiled pipe containing one fluid that passes through a chamber containing another fluid. The walls of the pipe are usually made of metal, or another substance with a high thermal conductivity, to facilitate the interchange, whereas the outer casing of the larger chamber is made of a plastic or coated with thermal insulation, to discourage heat from escaping from the exchanger. The plate heat exchanger was invented by Dr. Richard Sligman in 1923 and revolutionized methods of indirect heating and cooling of fluids. Dr. Richard Sligman founded APV in 1910 as the Aluminium Plant and Vessel Company Limited, a specialist fabricating firm supplying welded vessels to the brewery and vegetable oil trades. Design of plate and frame heat exchangers. The plate heat exchanger is a specialized design well suited to transferring heat between medium and low pressure fluids. Welded, semi-welded and brazed heat exchangers are used for heat exchange between high pressure fluids or where a more compact product is required. In place of a pipe passing through a chamber, there are instead two alternating chambers, usually thin in depth, separated at their largest surface by a corrugated metal plate. The plates used in a plate and frame heat exchanger are obtained by one-piece pressing of metal plates. Stainless steel is a commonly used metal for the plates because of its ability to withstand high temperatures, its strength, and its corrosion resistance. The plates are often spaced by rubber sealing gaskets which are cemented into a section around the edge of the plates. The plates are pressed to form troughs at right angles to the direction of flow of the liquid which runs through the channels in the heat exchanger. These troughs are arranged so that they interlink with the other plates which forms the channel with gaps of 1.3–1.5 mm between the plates. The plates are compressed together in a rigid frame to form an arrangement of parallel flow channels with alternating hot and cold fluids. The plates produce an extremely large surface area, which allows for the fastest possible transfer. Making each chamber thin ensures that the majority of the volume of the liquid contacts the plate, again aiding exchange. The troughs also create and maintain a turbulent flow in the liquid to maximize heat transfer in the exchanger. A high degree of turbulence can be obtained at low flow rates and high heat transfer coefficient can then be achieved. As compared to shell and tube heat exchangers, the temperature approach in a plate heat exchangers may be as low as 1 degree Celsius, whereas shell and tube heat exchangers require an approach of 5 degrees Celsius or more. For the same amount of heat exchanged, the size of the plate heat exchanger is smaller, because of the large heat transfer area afforded by the plates. Increase and reduction of the heat transfer area is simple in a plate heat exchanger, through the addition or removal of plates from the stack. Evaluating plate heat exchangers. All plate heat exchangers look similar on the outside. The difference lies on the inside, in the details of the plate design and the sealing technologies used. Hence, when evaluating a plate heat exchanger, it is very important not only to explore the details of the product being supplied, but also to analyze the level of research and development carried out by the manufacturer and the post-commissioning service and spare parts availability. An important aspect to take into account when evaluating a heat exchanger are the forms of corrugation within the heat exchanger. There are two types, intimating and chevron corrugations. In general, greater heat transfer enhancement is produced from chevrons for a given increase in pressure drop and are more commonly used than intimating corrugations. Flow distribution and heat transfer equation. Design calculations of a plate heat exchanger include flow distribution and pressure drop and heat transfer. The former is an issue of flow distribution in manifolds. A layout configuration of plate heat exchanger can be usually simplified into a manifold system with two manifold headers for dividing and combining fluids, which can be categorized into U-type and Z-type arrangement according to flow direction in the headers, as shown in manifold arrangement. Bashny and Martin developed previous theory of design. In the recent years, Wang unified all the main existing models and developed a most completed theory and design tool. The total rate of heat transfer between the hot and cold fluids passing through a plate heat exchanger may be expressed as Q equals WT(m), where U is the overall heat transfer coefficient, A is the total plate area, and a Tm is the log mean temperature difference. U is dependent upon the heat transfer coefficients in the hot and cold streams. See also, plate fin heat exchanger, heat transfer, LMTD. References. Bibliography Sadikakak and Hongton Liu. Heat exchangers, selection, rating and thermal design. CRC Press. ISBN 0-8493-0902-6. T. Kupan. Heat Exchanger Design Handbook. CRC Press. ISBN 0-8247-9787-6. J. M. Coulson and J. F. Richardson. Coulson and Reich Harson's Chemical Engineering Volume 1. Butterworth Heinemann. ISBN 0-7506-4444-3. External links, heat exchangers at DMOZ, plate heat exchangers, what they are and how they work, a list of published articles pertaining to plate heat exchangers, a screening method for the optimal selection of plate heat exchanger configurations by J. M. Pinto and J. A. W. Gutt, University of São Paulo, Brazil. Seeking the optimal design of a typical plate heat exchanger by Athanasios G. Canaris, Anikaterin I. A. Musa and Spiros V. Paras, Aristotle University of Thessaloniki.